So we are doing the so-called autocalculus. Okay, so that is just doing some kind of differential geometric business on the space of probability measures. Okay, and then of course here that differential geometry is the differential geometry of the Wasserstein distance, W2 distance. Okay, and then we considered the corresponding tangent spaces and the Wasserstein gradients and then gradient flows. The previous lecture. Today we will relate those Wasserstein W2 gradient and W2 gradient flows with uh, displacement convexity of functionals on the space of probability measures. Okay, how they are related. I mean, what implication this displacement convexity will have, let's say, on the gradient and then gradient flows. Okay, that is the goal today. Before we start the class, let me make some advertisements. So there will be workshop in Toronto next week, supported by Teams. Okay, so it's important. It is supported by Teams, but held in Toronto at Peace Institute. Okay. The title is Optimal Transport Stochastic Projections and Applications. I think the speakers there are really good researchers in these areas. So I really recommend you to attend those online lectures. So the lectures will be streamed, okay, online. And for that, you need to, I think, register for this event. So check this website. So the website is managed by Fizz. So this one, I think from there you can find the online lectures. But please also register through PIMS because it is PIMS supported event. All right. Okay. And so it's November 5, 6, and 7, Wednesday, Thursday, and Friday. And obviously, we will not have a class during those times. But I mean, attending these lectures is kind of a substitution of our classes. Okay? Good. Okay, remember what W2 gradient of a function on the space of probability measures is. So for that, I mean, you know that gradient is a metric dependent notion, and we are using this auto metric. Okay, auto. Namely, we represent the derivative of a measure with by the corresponding vector field via the continuity equation. Okay, and then the derivative of the measures are literally the tangent vectors in the space of probability measures, but we represent them by these corresponding gradient vector fields. And then the Riemannian dot product between them is given by this L2 type integral, but importantly, with respect to the measure rho you are currently at. So we are at rho in the space of measures, right? And then here we have these tangent vectors. And then so we are measuring the inner product between these tangent product at that location. And then this integral is with respect to that rho. So this is probably the only difference from the usual L2 product. Okay, then with respect to this metric, we can write down what gradient is using this like a directional derivative formula. And then, for each functional, the gradient will have, this product will have this representation, and then this representation will correspond to a specific vector phase gradient of some function corresponding to that gradient of the functional f. Questions? Yeah. I mean, if you compute this thingy, then okay, maybe it will be more clear if you see what gradient flow is. Okay, gradient flow is basically, I mean, ddt of xt is given by negative gradient of your functional at xt. So that is gradient flow. Okay. Okay. So in terms of the functionals on the space of priority measures, okay, the gradient flow is given by, I mean, the time derivative of the measure is given by negative of the gradient of the functional. So that is gradient flow. But when you write down this gradient of flow, we do not write this, but we write this. What is that? So this G is the vector field, I mean, back to your question, corresponding to this question mark. Okay. And then this is kind of conceptual equation, but the actual equation we use to consider the gradient flow is exactly this one. You find that question mark, the vector field corresponding to the gradient, and then you write down this continuity equation. So this gives the gradient flow of the functional f on this space. So this is basically a PDE, partial differential equation of this function rho. Rho. Rho is a space-time function. Okay. That's a great question. So yeah. Yeah. Yes. Yes. Yeah. So this sign came from that negative. Okay. It's a gradient descent, not gradient ascent. Okay. Okay, whatever it is, I think this is correct. Okay. Okay. So if G represent gradient, then gradient flow should put negative G. Okay. Yes. Okay. Oh, what? James, you should have pointed out this in the earlier lecture, right? We had that in the last lecture. Oh, so I just made the same mistake again. I'm sorry, it's my fault. Sorry. Okay. All right. So okay, so that's okay. This is just a review. Okay. Yeah, of course, I just put it there just to test whether you are following, right? Okay. And we saw examples, right? So the probably the most important way and fundamental example is this example of this heat equation. The heat equation is the W2 gradient flow of this Shannon entropy. Okay. And then we also consider this KL divergence. Okay, KL divergence is sometimes called relative entropy. Because the formula is almost the same as this, but instead of log of rho, you plug in log of d rho divided by d mu for some reference measure mu. That's why it is called relative entropy. And here, when the reference measure mu is given in this form, then the KL divergence or relative entropy is given by the usual entropy plus this potential function. Okay. Then the corresponding W2 gradient flow of this KL divergence is okay. So here now I'm fine. It's the gradient of this plus gradient this, but with minus. Put it in this continuity equation. So this is so-called the Fokker-Planck equation. And in the literature, the Fokker-Planck equation you see is of this form. F is some function. So then F satisfies Fokker-Planck equation if it satisfies this PDE. So this PDE, of course, looks different from this PDE. but they are equivalent. Just the relation is, yeah, here. This rho and this F are related in this way. Then this PD and is equal to this PD. So I'm checking that is, of course, your easy exercise. Okay. So there are, many such examples. Given a functional on the space of probability measures, you can consider corresponding W2 gradient flows, then you get some meaningful, important and interesting equations like this. Okay. So in other words, you can study or consider these meaningful and interesting and important equations from the viewpoint of W2 gradient flows. Okay. And sometimes you may have some, who knows, some kind of nonlinear PD of certain type, which you may not even know how to handle, in a usual, way you learn from your PD1 course. But then there are some kind of approaches that can still handle those kind of evolution equations, okay, using this optimal transport idea, feeding them into this framework of W2 gradient flows, okay? So, for example, then you will need to consider how to prove, let's say, existence of solutions of certain type of PDEs given as the gradient flow of certain function. Okay, for these, you have some other very well developed theory for existence and regularity and all these stability type regions. But who knows? There are some other PDEs given by this gradient flow framework with respect to the W2 metric. Okay, then, for example, one important thing is to show, let's say, existence of solutions for such gradient flows. And I think it's still a hot topic of research in PD theories. And that whole business started with around 2000, about 25 years ago. Yeah, maybe not 20, yeah, at least more than 20 years ago. And the key paper is this paper by Jordan, Kinderlea, and Otto. And now they, because of this name, these people's important work, they name their method as JKO scheme. So you will learn what JKO scheme is on Monday by Professor Parr. Okay, but that is in particular about proving existence of such solutions for W2 gradient flows of certain functions. Okay, am I making sense? Okay, so stay tuned. Okay, now today we will focus on the relation of W2 gradient and W2 gradient flows with displacement convexity. First, let's quantify this notion of displacement convexity. So let's say we have a functional on the space of probability measures, okay? And fix a number, lambda. Then we say such a functional is not just displacement convex, but lambda displacement convex if along any geodesic, along any W2 geodesic, so you have rho 0 and rho 1 in the space of probability measures, and you connect them by geodesics or T. And then along any such geodesics, your functional, then you, along that geodesic, your functional is now a function of T, right? Your functional will be a one variable function now in terms of T, will behave as a convex function, but with this lambda convexity. Okay? Yes. Where does S come from. So it was typo. Thank you. Thank you very much. So this is just a lambda convexity of just one variable function. Okay. So this lambda displacement convexity just applies the lambda convexity of the function restricted to any W2 geodesy. Okay. Is there any intuition on why the last term here, lambda convexity for the lambda? Okay, so that's a great question again. Let me try to do it. So example, so let's say lambda equals 1, okay? Then what is the most uh, well-known such lambda convex function? Okay, what should be an example? The easiest example of one convex function. Okay, maybe I should, so this is, so what this is actually the same as the second time derivative of f is bigger than of t bigger than lambda or equal to lambda. Okay, so it is just a t square over 2. That is one convex. Okay, and then it looks like this, right? And then if you pick 2 points here and there, sorry, now it's just in this case just between 0 and 1. So between 0 and 1, right? Then this part, this convex combination part gives you just a linear combination, just a linear function. And then this gap, okay? This gap, if you just do the subtraction, it looks like it's, maybe let me use 0 here, 1 here, like this. And this function is exactly t 1 minus t over 2. Okay, so that's, so for convexity, just usual convexity, you don't have this, right? That means your function is just below this kind of any linear combination in between. But lambda convexity says you have a more quantified gap between the linear combination and your function, okay? And of course, this gap is going, I mean, the graph of the function, lambda convex function goes below if lambda is positive, but when lambda is, lambda can be possibly negative in this definition. So in that case, it may go above, okay? But it doesn't go above too much. That is what this thing says, okay? So here, once again, this lambda can be positive or negative or 0. Good question. Any other question from the Zoom? Are you listening in the Zoom? Hello? Oh, can you hear me?
Yes, yes.
Oh, okay. So let me just make sure that this is second derivative. Okay. All right, and And you already saw this important example from one of the classes by Professor Paul, that on RD, when you consider this function, where this V has this bounded Hessian by this lambda, okay, then the corresponding Kullback divergence, which is basically, I mean, let me just remind you what this is. This should be integral log rho dx plus integral b d rho. Okay. So that is lambda displacement convex. So here, this entropy function is just just displacement convex. Okay. But this potential function, when this v has Hessian bigger than lambda, then together this becomes lambda displacement convex. Okay. Let me just say, note is zero displacement. Yeah, I don't think there's any lambda convexity known for this function, right? But it is just zero displacement convex, so it's just displacement convex. Okay, but then this functional rho 2 rho v d rho is lambda is displacement convex if Hessian of v is bigger than lambda. Okay, then if you combine these two, then you get, for the sum of this functional, you get lambda displacement convex. Okay. So KL with this nice measure is under this condition. Okay. Question about lambda displacement convexity? Any final question? So we just quantified the notion of displacement convexity by just plugging in this term here. Okay. All right. Then lambda displacement convex of a functional has important implication for the gradient flows. So once again, W2 gradient flow is given by this PDE. Okay. Of course, here we understand this gradient as its corresponding vector field. Okay, we have to be careful about that. But then, anyways, suppose we have functional and their gradient flows. Okay, so you have in P, I think P2x, you have one gradient flow, which is basically a curve in that space of probability measures, and another gradient flow, another curve, starting with the initial locations. Okay, then of course, I mean, without any other condition, they can do whatever they want, right? But suppose this F is lambda displacement convex, then the theorem says as time goes on, the distance between these points along the curve, between these two curves, gets smaller and smaller with this rate. Okay, I mean, of course, it gets smaller and smaller when lambda is positive. So you just consider first the typical case when lambda is positive. and it gets smaller and smaller. That is what this theorem says. Okay, so to illustrate, to give an illustration, it is like this. On the space, you have, let's say, some functional. Okay, it's a lambda positive case over your f. So f looks like kind of a strictly convex function, okay, on your space. And then you run, let's say, starting from somewhere and somewhere, you run gradient flow. That means you consider the corresponding point on the graph, and then you just follow the steepest distance. Okay, and then you have the corresponding curve rho 1t and rho 2t on the original space. And so this is like a bowl of your soup for your lunch, right? And then you have some, let's say, a bean placed. Okay, this is a bowl. You put two beans on your bowls, and then if the bowl has almost zero friction, then these beans will slide down, right? And then how they will slide down? They will slide down, they will slide down in a way that the mutual distance becomes smaller and smaller when the bowl is like in this like a convex shape. Can you imagine that? Do you understand what I'm saying? In other words, okay, you can view it this way. You consider the level sets of lambda convex one. Okay, maybe I should just consider the strict convex function. So this is just illustration, okay? They will look like this. So these are like convex sets. I mean, each sublevel set is convex. Each sublevel set is convex. So it looks like this. And then now you follow gradient flow. Let's say starting from here and there. Okay. Okay, maybe better to write draw more level curves. Then one should move this way. The other one will move this way. So, I mean, I just literally showed why this should happen. Then their mutual distance becomes smaller and smaller. But the thing is that we can even say the rate of such contraction. And that rate depends on this lambda for the lambda convexity. Okay, any question about this? So gradient flows in terms of your let's say measure is a PDE, but you can view gradient flows as curves in the space of probability measures. Okay, and as curves, the gradient flows are in this case when the functional is lambda displacement convex, then the distance between the points in the curve along the time gets smaller and smaller with this rate. Okay. Any question about this statement? Okay, so this illustration is the lambda positive case. I don't have good illustration for lambda negative case. Okay. this contraction theorem has an important consequence. For example, let's say, suppose you have two curves starting from one location. Okay. And each of the curves is a gradient flow of the same functional. Okay. And suppose the functional is lambda expressed convex, then you will not have basically two different curves having the same initial location. So that is the point of this remark. Because when the initial location is the same, this is 0. So all the following distances between the points along the curve is 0. It means those two curves are equal. So this gives you a uniqueness of the gradient flow. Okay. And this does not assume any sign of lambda. Any sign of lambda will work. So lambda positive negative case also works. Yeah, so that is great question. So let's remember gradient flow is basically an ODE given by this. Okay. So this is ODE. Okay. So if the curve is on RD, Euclidean space, then you have nice existence and uniqueness theory of this ODE. Have you proved it yourself? Do you remember the proof? But I think you can just open a book of any OD, any serious OD book, then it will give a proof. The proof is not that trivial, in fact. It means the fact that you even have a existence of such solution is not that trivial. Okay, of course, that proof, existence proof also gives uniqueness. So such existence and uniqueness of OD is not trivial. Okay, that's even on RD. Now, here we are on the space of probability measures, highly infinite dimensional space. There, proving any kind of existence and uniqueness of an OD is, I would say, maybe believable, but not trivial. And I don't have any concrete example in mind, but sometimes it's not true. You may not even have existence, and even if exists, you may have a non-uniqueness. That's why people, I mean, okay, so it's ODE if you just view it as like a curve on your space, especially if the space is RD, but on function space, such an ODE is basically PDE. We are talking about then existence and uniqueness of solutions of certain PDEs. That's not always easy to verify, and even sometimes it's wrong. A great question. It's a very important question. Yeah. Okay. So on PX, it is a PDE. I mean, on PX, it is an ODE, sorry, it's an ODE, but in terms of rho T, it is a PDE. Okay. Okay. Of course, this is for the same functional. With different functionals, of course, you may have different gradient flows. All right. Another thing is, and I mean, this is like contraction. For example, if in particular when lambda is active, then this rate, I mean, you will get smaller and smaller distance between the points along the curves as time goes on, right? So this is then of course then if you consider the flow of this gradient flow, I mean given rho, you can run it by time t, and if you have another rho prime, you can run it for another time t. So then for those initial points, you have flow getting these finite points. Okay, so you can view it as a mapping on the space. Okay. From rho to rho t. It's a mapping. And this mapping, if lambda positive, gradient flow, the gradient flow as a mapping is a contraction, right? As just this formula suggests, it's a contraction. Okay, then the mapping is contraction, then you learned from your undergrad analysis course, this one of the most important theorems in analysis, contraction mapping principle. Do you remember that? And James, do you remember? Sorry.
Yeah. Complete vector space is a contraction type. It reaches long to one to that one. That's the limit. It is every code. You have limit.
So if you iterate the contraction, then you do have limit, and that limit is just one single point, and that is the only fixed point of that mapping. Okay, so that is contraction theorem. So that means this flow, you will run this flow from other points, right? Then they will all converge to some final destination, which is a fixed point of the flow. I mean, not a, the unique fixed point of the flow. Okay. Of course, this requires a completeness of the space, but I hope you did the exercise of proving completeness of the P2. Okay. But anyways, under the completeness, you can apply contraction mapping theorem so that you have a fixed point. Okay. Then these every points will go to as t goes infinity to this fixed point, and then you can see the rate of convergence toward that fixed point out of this contraction theorem, right? Why? Because you can just put the second gradient flow to be starting with the fixed point, then it does not move. So just that one point, the staying one point is just a gradient flow, the stationary point. Then that is rho infinity. So then their distance is just decaying in this way. So you have this exponential decay, exponential convergence toward the fixed point when you have this contraction. Okay. Yeah, so this is for not just only geodesy, for any gradient flow with lambda displacement convex function. Yeah, every time. Yes, right. And so again, so this is the result of PDE. So that means on evolutionary PDE. So it's a not just PDE, it's on evolutionary PD. I mean, it's just time-dependent PD. I mean, it's kind of so-called parabolic PD. Okay, so this evolutionary PDE has this like a stationary solution, and then every other solution to the PDE converges to the stationary solution, and the rate of convergence is given in this exponential rate. Okay. Yes. Yeah, we are going to talk about that. Okay, thank you for your, what? Oh, yeah, of course, yeah, of course. Yeah. So let's then talk about how we prove this theorem. Okay, so now I think you have enough interest to see the proof. Okay, so what's the proof? So first, let's just consider the idea. Okay, the idea is extremely simple. I mean, every second year calculus students, maybe not everybody, every second year calculus students who studied well enough will be able to prove this in that baby case when our function is a function on RD. So let's just do that. So F is RD. Okay, then the gradient flow is this. X, the time derivative of the xt is given by negative gradient of F at that point. And we have, suppose we have two gradient flows, okay, of F. And here we are assuming that this F is lambda convex with this lambda, okay? So this Hessian is bigger than or equal to lambda times identity. Okay, then let's just look at the distance between these two two points along these gradient flows. Okay, I mean here gradient flows in this case are just curve xt and yt moving. Okay, then let's just compute its derivative. If you differentiate this, you get just this. Just the usual product rule of the derivative. So you have this derivative on one argument, but now times two because of this two. But this one, you can just translate it into this gradient f using this formula for the gradient flow. So you have this. But then it's a gradient of f. Now you can write this as an integral of the Hessian. Okay, because Hessian is a further derivative of the gradient. So I'm just using the fundamental theorem of calculus. This gradient is integral of the derivative of that gradient, which is just Hessian. Okay, so you have this formula. And this is am I making sense here? So basically you have this. You have this xt and yt, and then you just consider a line segment from y, actually is from y to yt to xt. And then along this line segment, you differentiate the function, this gradient of f, then you will get this Hessian of f dot with this directional vector. And then you just integrate in time. Then you get just this difference at the end. So this is just a fundamental theorem of calculus. Okay, then now we see the Hessian. The Hessian is assumed to be bigger than or equal to lambda. So then this whole thing, this lambda times identity. So this lambda times identity times that is the, because of this minus, is the upper bound of this quantity. So you get this. But then what you get is just the derivative of f in t is negative 2 lambda times f itself. Okay, so you get f prime t is negative minus 2 lambda constant times ft. So this means you can just apply Gronow, or just a simple ODE, then you can prove that ft is actually decaying in this way. So this is very easy computation. And basically this is the idea why we should have such contraction. Okay. if you are a geometric person, of course, the idea is just already here. Geometric idea is here. Just the Hessian being Hessian of f being lambda is like these Lebesgue curves has curvature lower bound. Okay, so it can kind of round. Then you just follow the orthogonal directions of these round Lebesgue curves. Then you will have this kind of contraction property. But of course, I mean, then it's not so easy to derive such a rate from just this geometric shape. So to derive such a rate, maybe better to go with this analytic computations. Okay. Question? Any question from the Zoom audience? Is everything going well? Okay. You need more time to take a note? Okay, just let me just wait. So this kind of simple idea, ODE idea, will lead us to this non-trivial PDE results. But of course, to carry out this ODE idea in the context of this infinite dimensional space requires some care, right? So second year students can handle this, but I don't think they can handle the actual functional space computations. Okay, so, but because we are graduate students, let's just try to do that. Okay, so now let's try to be more rigorous. Okay. All right. Okay, I'm going to follow the book of Ambrosio, Gigli, and Savare. Sorry, I made a typo here. It should be only one L. Okay. In chapter 11. Okay. Basically, the idea is just here. It's just a matter of how to make more rigorous treatment of these ideas. And they came up with this idea of replacing, where is it? Replacing the ODE, what is ODE? So first, ODE is its time derivative is minus gradient of W2 flow. So this is a gradient flow, right? T. So this is like ODE. So basically it is EX ET equal to negative gradient of F XT. It's ODE with an inequality like this. Of course, this one has some derivative, but now in time. In the gradient flow equation, you have to differentiate your functional F, okay? But somehow they decide that maybe it's better not to do that. And then instead just replace this with certain inequality. Now, assuming lambda displays convexity. So what they say is, if F is lambda expression convex, then rho T being the gradient flow of that F is the same as, I mean, not exactly the same. It implies this inequality. Okay. So such inequality is called evolution variational inequality, or EVI. It is now named. I mean, the people in the gradient flow business, they use this very often. This is kind of fundamental concept for them. Okay? Okay, the point is that here you don't see the derivative of F. Okay. So in other words, if we can turn this gradient flow in property into such inequality, you can consider those functionals which are not necessarily differentiable with respect to associative metric. Okay? Make sense? At least you can write down some kind of notion for being a gradient flow. And here, then why we have such weird looking inequality? Here you have this quadratic term in associative distance, and then this time derivative of this associative distance. Yeah, why do we have that? Let me explain. So let's see. You have, let's say, P2AC. I'll just simplify Px. And you have some functional F. Okay. And then you have, let's say, yeah, you have a point sigma, which is a measure, and another point rho T, which is on a measure. Okay, then, okay, so this is obviously this picture kind of assumes that this lambda is positive, but I mean here in these computations, I mean lambda is just some real number. Okay, lambda is a real number. Okay, what is it? What is going on? So here, okay, let's just focus on this case, lambda positive case. Okay. Then the function should look like a convex function, right? So then, in particular, you can consider a line segment connecting rho T to sigma. Okay, and along that line segment, the function is indeed lambda convex. That's what lambda convex is. Along each geodesic, you have lambda convex function for the restriction of your functional on that geodesic. Okay. Then, because it's lambda convex, if you assume that the function is differentiable, then you can consider this supporting line. But this supporting line, which is below this F, should look like this. Here, this is a value at that point. This is just a derivative of that line. And then this term is, I mean, this is just a linear function. Okay? So this is the supporting line, okay? And then lambda convexity will give you this gap. This gap is given by lambda over 2, W2 rho T sigma. Okay. So this is like the linear term and this quadratic term, then this lambda complex function is above that, that approximation. Okay. So this is just calculus, but of course, here f is, and you can consider more than more general f that are not necessarily differentiable because, for example, you consider this so this like sub-differential business where you can kind of give some notion of derivative for those functions not necessarily differentiable. So this function may not necessarily differentiable, can still be lambda convex. Convex functions are not necessarily differentiable. The same for lambda complex functions. Then here, instead of derivative, here what you get is some kind of sub-differential, sub-gradient of the function. But that is what this Ambrosio Gigesaber book did. But for now, for us, let's just assume that everything is differentiable. So we can just write down this as gradient dot with the velocity of this geodesic. Okay. So far, so good. So this is just this, and this is just nothing but this geodesic, which is nothing but negative gradient of the this Wasserstein distance. That is what you learned from lecture, I think 13, right? If you follow a geodesic, the velocity of that geodesic is the same as the W2 gradient of the distance function. That is what it is. Okay. And because of that, on one hand, this term here is nothing but its gradient with this, I mean this derivative and this gradient and this. So this term is the same as negative mu as this negative velocity. And on the other hand, this term is this with that. So that means if you really play with these terms, am I fast? It's okay? Then you can just verify this is exactly the same as this. By just comparing these lines. So that's why you can just plug in here, this. So you get this inequality. So that's the step one. Okay, then what is step two? Step two is some kind of calculus lemma. Okay, this is really calculus lemma. Okay, you have some function depending on two variables, and then for each variable you have this kind of absolute continuity property in each variable. Okay. Then if you consider this function having the same t and t in both arguments, then the derivative of this function which is basically, I mean, you have, let's say you have a differential function t, then if you differentiate this in t, then you get on one hand, there's partial derivative in one argument and plus the partial derivative of the other argument. Okay, but this is when the function is like differentiable. But so here, okay, of course, this notion means it's yeah, this is like this means the usual thing, h goes to 0, delta t plus h divided by h. Okay, so that limit or lim sub of that is bounded by lim sub of each fractional limits corresponding to the derivatives. Okay, so this is like some lemma which is believable, but but you can check the proof. Okay. Okay, then step 3, finish the proof. So you just define this dst as the distance between these two the points along these gradient flows, but with possibly different time s and t. Okay, so this is two variable function, and then the step 2 says this thingy. I mean, the reason why we are doing this business is because differentiating Wasserstein distance is not always straightforward or trivial. So that's why we are kind of using this, assuming possible non-differentiability of the function. But anyways, if you differentiate this, then you get this from step 2, this. But then this and that. So this is basically the derivative of this guy in only one argument. So this term corresponds to basically this. Okay, it just differentiate. So fix the other one and just differentiate in one argument. Okay, for your Wasserstein distance squared, and you get this expression. I mean, from step 1. So this term is less than or equal to this. This is from step 1. So then you can replace these with these expressions imbibing the functional and this Wasserstein distance squared. Okay, let me just be quick now. Then you get this whole thing, which is this one. We started with is less than or equal to this, and each of them is twice of this and that. But if you take the sum of these, then these guys and these guys are cancelled. So what remains are this thingy, so which is basically 2 times of this term. So what you get is a function, the derivative of a function is less than or equal to 2 times of lambda times that function. And from there, Gronwall implies this inequality is not Gronwall. What is the correct spell? Yeah, sorry. Okay. So then you have this. Okay. And these steps will be more suitable when you consider a less differentiable situation. Okay, but if everything is super nice and super differentiable, then just the original original idea on just RD, I think will still work the same. Okay. Okay, I still have 20 minutes, slightly less than 20 minutes. So let me continue. Okay, any questions so far? Oh, second lemma, it's just, the intuition is just here. If you differentiate two variable function, but with the same value at both arguments, with that argument, then what you get is this is just what the chain rule. Is it chain? It's called chain rule, or you just have a derivative of one argument and derivative of the other argument. Okay, this should be like equality if everything is super nice, but then this theorem says it's inequality. Quotation means this is not exactly the partial derivative, because the partial derivative may not exist. It's a rim soup. Yeah, good question. Other question? So the step 1 and step 3 are clear. That's why you ask only about step 2, right? Yeah. Okay. Okay, so then let me continue. I posted this note, so okay, now, so this is we will do some precursor of what Professor Fa will discuss more extensively, namely the relation between displacement convexity and functional inequalities. Okay? So we know what displacement convexity is now. Okay, what are those functional inequalities? Okay, but you will see. So let's focus on the case when the underlying domain is RD, and let's just consider our reference measure mu to be e to the minus b, and assume that the Hessian of V is bounded by this lambda, and lambda is some number. Okay, this means the Kullback-Leibler divergence is lambda displacement convex. Okay, so assume this. Then we have the following inequality. And these are not about gradient flow. These are just something separate. Okay, we have this so-called HWI inequality, namely the difference of Kullback-Leibler divergence is less than the gradient of W2 gradient of Kullback-Leibler divergence at one argument. Okay, I think at row 1. I hope this to be correct. And then times the distance between them. Okay. So I'll give you an intuition why we have this. But before that, here the W2 gradient of the Kullback-Leibler divergence is basically this vector fields, which is given by logarithm of this Radon-Nikodym derivative between rho and mu. Okay, so remember, so here KL rho mu is given by this formula. So it's a logarithm of d rho, d mu, d rho, and this one is nothing but gradient of this function here. Okay, and this W2 norm of that gradient of W2 gradient of Kullback-Leibler divergence, which is this, has a special name, It's called in the literature, especially in statistics, Fisher information. Okay, so Fisher information has this formula. This is probably is relative Fisher information, but anyway, so Fisher information of rho relative to mu is given by this formula. You just take norm square of gradient of logarithm of the relative density of rho and mu, and then integrate with respect to rho. Okay, so that is exactly the same as this expression. Okay, and this is some important quantity they consider in the literature, the statistics or probability. Okay, and then you may wonder why this inequality is called HWI inequality. Okay, so I is here. This is I. Okay, W is here. Also send this W. And where is H? So here the KL is sometimes called relative entropy. For entropy, in physics, I think especially in physics, they use H. So H is KL. Okay. Okay. So now I explain why this name. So HWI inequality. Then why we have this inequality? And where is this displaced convexity relevant? Okay, so here this HWI inequality assumes only lambda non-negative, so just the displacement convexity. So why do you have such inequality? Okay, let me explain. So let's say here, let's consider rho 1, rho 2 in the space of priority measures, right? And then, so KL, in this case, when lambda is non-negative, is displacement convex. So it is like a convex function. So its graph will be like this. That is KL. This is R. Okay. Its minimum is at 0 when at mu. The minimum is 0 at mu. But anyways, it looks like a convex function. Then you can draw. I'm just giving some intuition. Okay, intuition. You can draw the supporting hyperplane. Okay. Then this supporting hyperplane looks like what? It is like what? You have the derivative of KL and this thingy, the vector between rho 2 and rho 1 plus that's basically what it is, right? Plus KL rho 1. Okay, so this is so KL at rho 2 is bigger than or equal to let me resize this. I'm just ignoring this mu from the formula. So here. Okay, let me explain. So this quotation mark means this vector between rho 2 and rho 1. Of course, there's no such vector in Wasserstein space. I'm just considering the geodesic between rho 2 and rho 1. Okay, and then corresponding velocity vector. And then this KL, this gradient is just the Wasserstein gradient, W2 gradient. And this is just a value at of KL at rho 1. So because of convexity, we have this formula. Then this minus this is here, but now you have, you see, you have the kind of the negative direction, right? So this is KL rho 1 minus KL rho 2. So KL rho 1 minus KL rho 2 is less than or equal to this quantity. And then this quantity using Cauchy-Schwarz is because it's inner product is less than or equal to the norm of each of them. So that's what this why one can expect such inequality, the HWI inequality. Okay, make sense? Okay. Let me be faster because I don't have much time left. Okay, then when lambda is positive, there's this very famous Lagrange inequality. Lagrange won Nobel Prize last year, right? So, but P equals 2 case. What is it? It means the following. So KL in that case, KL in this case is lambda convex, but lambda is positive. So it is kind of strictly convex. It behaves like the quadratic function. Okay. And then you have, so this lambda convex function has bigger values than this quadratic function in lambda, bigger than or equal to, bigger than or equal to. So this function, the KL, is bigger than or equal to this function. That's what this is. Make sense? Okay. So that's Lagrange inequality. Of course, I mean, I just gave illustration, but not a proof, but the idea is there. Okay, then, so we have this HWI inequality and Lagrange inequality. They are a manifestation of this convexity or lambda convexity of KL with respect to the W2 metric. Okay, that's it. But then if we combine this inequality, then we get something nice, interesting too. So this KL square, and this we have this when rho 2 is just mu, this is 0. So rho 2 is just mu. So then KL square is less than or equal to this squared and this squared. So this is from HWI inequality when with rho 1 rho and rho 2 u. Okay. But then this one, this part is from the Lagrange. W2 is less than or equal to KL with this factor. So what you get is this inequality, just this one. So it means KL is less than or equal to the Fisher information. This is Fisher information up to some constant. So this is really famous inequality. I mean, even though it looks simple, in probability and statistics and in mathematics in general, it's called log-Sobolev inequality. Okay. So the reason why it's called a log-Sobolev is because why Sobolev? Because this Fisher information term has this derivative. Okay, and why log? It's obvious we have many logs here and there for KL and Fisher. Okay, so that's why it's called the log-Sobolev inequality. And very important part of this log-Sobolev inequality is this. So if you consider Sobolev inequality, the inequality is kind of similar. You have some kind of integral without derivative, some kind of integral with derivatives. That's what basically what Sobolev inequalities are. But there, these coefficients in usual Sobolev inequalities, they depend on the dimension. And the larger the dimension, the worse the such constant. Log-Sobolev inequality does not have any dimensional dependence. This is really the key property why people really like log subgraph inequality. So you can apply it to very high dimensional situations. So it has application to like information theory where they need to handle, or machine learning, they handle high dimensional spaces or high dimensional information. So that's one of the reasons why people are fascinated by log subgraph inequality. Okay, just one last comment. This is not the original version of log subgraph inequality is not sharp. The sharper version has this constant 1/2 lambda, and getting that sharper version is your exercise. And then I just outlined what to do to get the sharper version. But you are not that far from the sharper version. So yeah, even this one is already great. Okay, so maybe I should stop now. So this is lecture.
In other words, for